So thank you very much for giving me the floor to welcome the participants of this webinar, which is actually the 8th out of 9 of the series of regional webinars that the IEG have organized during the International Geomorphology Week 2022. This is the 3rd International Week that we've been organizing. So far it has gone really successful, and of course this is also due to the dedication, the strong dedication that someone like our Vice President Susan Conway had for this event. So she worked a lot behind the scenes for a few months, and she was in touch with the coordinators of all the events to set up a program that is really a striking one. So far I have attending all the webinars. I don't know if there is a prize in the end, but I was there at every meeting, and I can tell you that with different approaches, with different ways of communicating science, I heard exciting talks. Many of them were provided by early career scientists and young geomorphologists, so I was also happy about that, and the same will happen today. So I think that there is a promising future for geomorphology and for the IEG, of course. So I'm really glad to the speakers that have given their availability to talk today and during the other events. Please have a look also at the other side events that have been planned during the week. A few are still to be held, and I would like to mention the last one of the series, which will be on the 8th of March, and it will be the second workshop for women in geomorphology. So there will be speeches, talks given by very promising and also from senior geomorphologists. So you will see how large the contribution of women have been in the past, and how even larger will be in the future. So I don't want to steal any more time to this event. I would like to ask Susan if she would like to say something, maybe invite all of you to be in Coimbra next September. Please, Susan.
Thanks, Mauro, and thank you for the introduction. Sorry, this would be my speech at the end, so I'll make it really, really quick so that you guys can get on with the exciting talks that are going on today. Yeah, just like a quick word about the biggest event in the IAG's calendar coming up in September. So 12th to 16th of September in Coimbra in Portugal will be the International Conference for Geomorphology. So really big event in the calendar, really big event for geomorphologists all over the world. The abstract deadline is in just under 2 weeks. So if you haven't already put your abstract in, then think about putting that in. I'd like to highlight as well for all of you who are maybe studying or in an earlier part of your career, or maybe think you don't have enough money to attend the event, the IAG will be providing grants, and there'll be more details about those coming up soon. But just to say that they're upcoming, so they're not actually advertised on the website at the moment, but they're upcoming. So please keep an eye out for those if that's something that's going to interest you. Just 2 very quick points about Coimbra as well. Why is it such an important event? It's not just such an important event because we bring together some fantastic science from around the world, but also it's a highlight of the IAG's calendar because we renew the executive committee at the international conference, and also we decide on the next IAG conferences that are going to be coming up. So this is your opportunity to influence the IAG, either in becoming more involved in the workings of the IAG, or in proposing a meeting for us to hold in the future. And this is not the the executive committee that imposes it on you. It's you, the community, that tell us what you want in the next 4 years. So I really encourage you to engage with those 2 points. Right, I'm going to stop there, and please, with 2 more minutes remaining before the program officially starts, I will let Manu take over again. Thank you very much, everybody, and enjoy.
Thanks, Susan, and also Mauro for the welcoming words. So now we can begin the session. The session is organized by different national scientific members of IAG, which are Belgium, France, Switzerland, the Netherlands, Germany, and Austria. Unfortunately, Austria could not really participate this year because of another event in Austria in parallel, and finally there was nobody from Germany. Concerning the program, I have to inform you that the last talk won't happen, Jonathan Bussard, because he is sick, and he has waited until today to decide that finally he won't be able to participate. We are still in COVID time, so I apologize for that. So we can begin with the first talk by Chantal Del Siro. She holds a PhD of the University of Lausanne in geomorphology, and now she's working at the University of Applied Sciences in Canton Ticino in southern Italian-speaking Switzerland. And I give the floor to Chantal. You can share your screen and begin your talk. Thank you.
Okay, so good morning to all and welcome to my presentation. In this talk, I will present you the main result of my master thesis, whose title is Water Origin and Quality of Rock Glacier Springs, Case Studies in the Swiss Alps. I start with a little introduction. So this work is part of the global theme of permafrost degradation in relation to the ongoing climate change. Permafrost degradation can also affect water resources. Indeed, it seems that rock glaciers are becoming increasingly important sources of water due to the progressive melting of the ice body. But a lack of understanding of the hydrological functioning is observed in the scientific literature. And in particular, the origin and the quality of the water emerging from rock glaciers are not well known, together with its contribution to aquatic systems. This uncertainty about the hydrological role of permafrost degradation is related to the fact that ice melt tracing in rock glacier outflows is an indirect and technical difficult task. Indeed, only a small number of studies try to detect the water supply related to the ice melting in rock glacier outflows through some physical and chemical parameters. In particular, they use as potential ice melt tracers the delta O18, which allows to detect and to explore the water origin of the water emerging from rock glaciers, and also the electrical conductivity and ionic content in order to evaluate the impact of ground ice melting on the hydrochemistry of aquatic systems. So the goal of this study is to improve knowledge about ice melt tracing in rock glacier outflows through physical and chemical tracers in order to understand the hydrological role of rock glaciers in periglacial watersheds. Two research questions can be defined. So is the chemical and isotopic composition of rock glacier springs different from that of streams not fed by rock glaciers? And can analysis of the physical and chemical composition of rock glacier springs determine the water origin during the warm season? So to answer these questions, we have chosen 6 study sites, which are located in the Swiss Alps. We have the sites of Lac des Vaux, which is located in the canton of Valais, and where there is an active rock glacier. And then we have the other 5 sites, which are located in the canton of Ticino. The first site is Lago Nero, where there are some ice patches and an active rock glacier. We have the sites of Lago di Leit, where there is an active rock glacier. The sites of Val Cadlimo, where there is an active rock glacier. The sites of Alpe Piai, where there is a transitional rock glacier. And finally, the sites of Valle di Cero, where there are some relict and active rock glaciers. For each study site, we have analyzed 2 types of water source. The sources called RG, which is a rock glacier, so they are fed by rock glaciers, and the sources non-RG, so non-rock glacier, which are not fed by rock glaciers. So what did we do at these sites? First of all, we did an electrical conductivity monitoring of RG springs. We also did a manual water sampling 3 times during the warm season, the first time in early summer, the second time in late summer, and the last time in early autumn. And with these water samples, we did some chemical analysis in order to determine the major ions content of the water, and also some isotopic analysis in order to determine the delta O18 of the water. And finally, we also did an automatic sampling at the RG spring. And with these water samples, we did some isotopic analysis in order to reconstruct the daily evolution of the delta O18 of the water. So I show you now the main result of this work, and I start with the electrical conductivity measured in RG springs. So here we have some graphs showing in black the electrical conductivity measured during the warm season. There is also a blue dotted line, which is the trend line, and allows to see the seasonal trend of the electrical conductivity. And here is interesting to observe that the water emerging from active rock glacier and ice patches is characterized by a seasonal increase of the conductivity. In contrast, the water emerging from the transitional rock glacier of Alpes is characterized by a seasonal decrease in conductivity. And finally, the water emerging from the relict rock glacier of Cheru is characterized by rather constant values. I show you now the result of the chemical analysis, and in particular the ionic content in sulfates, calcium, magnesium, measured in RG and non-RG springs. So here we have the graph showing the concentration of sulfates, calcium, and magnesium measured in RG sources on the left and in non-RG sources on the right, measured in early summer, late summer, and early autumn. And here is interesting to observe that in the sites with active rock glacier and ice patches, it's possible to observe a clear seasonal increase of concentrations in RG sources during the warm season. In addition, it's also possible to observe that the concentrations measured in RG sources are bigger than those measured in the non-RG sources. In contrast, in the sites with the transitional rock glacier of Alpes, in general we observe low concentrations. In addition, there is not a clear seasonal trend of the concentrations. And finally, the concentrations measured in the RG source are similar to those measured in the non-RG source. And regarding the relict rock glacier in Valle di Cheru, in this site we have observed high concentrations, but the concentrations measured in the RG source are similar to those measured in the non-RG source. So to sum up a little bit, we observed a seasonal increase in electrical conductivity and in the ionic content in the water emerging from active rock glacier and ice patches. So how to explain this ion enrichment? During the warm season, there is an increase in the seasonal top depth, which can cause, in one hand, an ion enrichment through the chemical weathering, because there is an increase in the freshly exposed rock surface within a rock glacier. But in our study, the watersheds are characterized by gneissic rocks, and gneissic rocks normally don't promote the chemical weathering. In addition, we also observe that the flow tends to decrease during the warm season, which means that there is a little water rock contact within rock glacier in early autumn. So on the basis of these observations, we suggest that the chemical weathering probably doesn't play a major role in this ion enrichment. On the other hand, the increase in the seasonal top depth can also cause an ion enrichment through the ground ice melting, because the ice can serve as temporary store sites for atmospheric deposits. So once the ice melts, these chemical elements can be released in the water. And so we suggest that this ion release process is the dominant process of this ion enrichment that we observe in this study. I present you also the result of the isotopic result, and in particular, the isotopic signature that we measured in the Geoarchaeology spring. So here we have a graph showing in black the evolution of the delta O18 measured in the Geoarchaeology spring. In blue, we have also an isotopic value for the snow sample. And here is interesting to observe that in early summer, the water emerging from the rock glacier has very low isotopic values, and these values are very similar to that measured in the snow sample, which means that in early summer, the rock glacier outflow is mainly fed by meltwater coming from the snowpack. And then we observed an O18 enrichment followed by a stabilization of the values, forming a plateau. This isotopic enrichment can have different causes. First of all, the fact that we have no more snow melt, so we have no more water supply related to the snow melt, which is depleted in O18. And during the season, we have also an increase in water supply related to the groundwater, which is mainly fed by rainwater, which is enriched in O18. And finally, we suggest also that we have an increase in water supply related to the ground ice melting. And this water can be enriched in O18 because the ice can be subject to several melt freeze processes that can enrich the ice in O18. Anyway, we must be careful to use the delta O18 as an ice melt tracer, because we observe this isotopic enrichment in RG and in non-RG sources at all study sites. Finally, I present you a conceptual model which is based on the result of this work and which aims to explain the hydrochemical process that occur within an active rock glacier. So first, we are in a cold period in the past, and we have an active rock glacier. The atmosphere can contain different chemical elements, such as sulfates and calcium. And during precipitation, and especially during snowfall, these ions can be transferred, firstly in the snowpack, and then to the soil through a refreezing process of the meltwater. The final result is that the frozen ground can store different chemical elements into the ice. We are now in the present time, and in particular in early summer. We have always our active rock glacier with an active layer which can contain some seasonal ice. The suprapermafrost flow is dominant, and it is mainly fed by meltwater coming from the snowpack. If we have a look at the physical and chemical composition of the water, we can observe that the water has low electrical conductivity values, is depleted in O18, and it has a low ionic content. We are now in the late summer, and we have always our active rock glacier with an active layer that contains less seasonal ice. The snowpack is completely gone, so the heat produced by solar radiation can penetrate into the soil and increase the subsoil temperature, which promotes the ground ice melting. And if we have a look at the chemical and physical composition of the outflow, we can observe that the water has medium values of conductivity, is enriched in O18, and it has a medium ionic content. And these values could show the beginning of the ground ice melting process. And finally, we are in early autumn. We have always our active rock glacier with an active layer that no longer contains ice. And the physical chemical composition of the water shows that the water has high values of electrical conductivity, is enriched in O18, and it has a high ionic content. And these values could show the water supply related to the ground ice melt. So thanks for your attention. And I don't know if there are any questions.
Thanks a lot also to the IAG for inviting me. So I'd like to give an overview on mountain biogeomorphology, what I've been working on the past years. I'm trying to answer the questions what plants do on unstable mountain slopes. Yeah, coming back to the mountains, you probably, as a geomorphologist, will firstly see in this picture a lot of rock glaciers we just talked about. So these ones, there's a bit of thermokarst, which we can see as a geomorphologist, probably a bit of rockfall and nice Taylor slopes you can see here. There might be a few debris flows happening here, a bit of landsliding maybe, some erosional processes, so we can really see mountain slopes. They are very unstable from a geomorphic point of view. Possibly there are also a bit of periglacial processes, so solifluction here. If, however, we look at it from an ecological point of view, we see that there's not only vegetation, but if we were an ecologist, we would also see or expect that there are different types, different species of vegetation here, pioneer species, maybe dwarf shrubs at different locations. If we zoom in a bit more into this area, we can see here on the front of this not so active anymore rock glacier that plants manage to colonize it. And they even affect the processes on this rock glacier front because they really create these very small steps here. So we have a bit of step slope profile here. So I think what we can see already or expect that there are feedbacks between the geomorphic processes and the plants in the alpine environments. And that's actually what we're looking at in biogeomorphology. So these feedbacks, these biogeomorphic feedbacks between organisms, so not only plants, but also animals, ecological processes, and our geomorphic systems, so the geomorphic processes, the landforms, and the material properties. Why is it important to study mountain biogeomorphology? As we all know, mountains are very strongly affected by climate change, and this climate change is affecting both the geomorphic system, where we expect to have more hazards, no natural hazards in the future from geomorphic processes. At the same time, climate change also threatens mountain biodiversity because the plants have to migrate upslope to survive, and maybe that doesn't work. And what happens in the future really depends not only on the effects of climate change on the individual parts, on the ecosystems and the geomorphic system, but also really on the feedbacks between these systems, and they are not so well understood yet. So in my talk, I'd like to answer the questions, what do plants do on unstable mountain slopes? So we're going to look at how do plants survive and affect mountain slope movements? Under which conditions can biogeomorphic feedbacks occur on mountain slopes? And we will also have a look at if mountain plants can create landforms and if the geomorphic and ecologic development of mountain slopes are coupled. Okay, how do mountain plants survive and affect slope movement? Well, to do so, plants on moving alpine hill slopes, mountain slopes, like the one we saw on this rock glacier front, creating these small steps, they need adapted traits. They need traits, so-called response traits, to survive slope movements. So like, moving the slope, creeping low, they have maybe can be hit by rocks, they can be buried by sediments, so they can tolerate sediment burial and slope movement, and they are also often very well adapted to really creep over the moving debris and stabilize it. So these are important response traits of this alpine vegetation. At the same time, we can expect that these slope plants will also stabilize moving slope, which happens through effect traits. These effect traits are, for example, roots, which create root cohesion and thereby stabilize the slope. These plants, they increase the surface roughness and thereby decrease the flow velocity and can trap fine sediments. And they can also even have thermal effects. So for example, Dryas octopetala, which is pictured in all of these pictures, a small alpine dwarf shrub, it builds up very thick mats, so about organic mats, about some centimeters thick, you can see here. And we expect that this can affect the thermal transmission into the soil and affect how the soil freezes. So through all of these effects, the plant, Dryas octopetala, will affect the moving hill slope. And plants that have these effect and response traits and can interact with slope movements are so-called ecosystem engineer species. So that's the first important term to note. So now we know, okay, plants can survive, a lot of alpine plants can survive on moving slopes and they can even stabilize them. However, if we look back at these pictures from a geomorphic point of view, we would probably say, oh, where are your plants here? So all of this is really unstable, probably no chance on the rock glacier for these small plants to do anything. Probably no chance on this very active Taylor slopes. So what are the conditions for these biogeomorphic feedbacks to occur? Basically, this depends on the relationship between the process activity, so the magnitude of the process, and its frequency, and how well the plants are adapted to these geomorphic processes through their functional traits. So the species resistance, they can resist the process, and if they can quickly regrow after it, so the resilience. To investigate these conditions for biogeomorphic feedbacks, we sampled 50 vegetation plots, so really 2 × 2 meter squares on little moraine slopes in Turtman Glacier foreland, and noted which geomorphic processes occur there and which plant species occur there. What we found using multivariate statistics is that with very active geomorphic processes, for example, gullying and debris sliding, we mostly find pioneer vegetation. If for dwarf shrubs, they often grow with a lower, like Dryas octopetala, with a lower geomorphic activity in solifluction processes, and shrub species really dominate on stable slopes with no activity. Based on these relationships, we developed a concept of a biogeomorphic feedback window to identify the conditions for biogeomorphic feedbacks, in which we relate the process magnitude and ecological severity of the processes and their frequency to this resilience and resistance of our plant species. If we have very highly geomorphic activity, for example, by debris flows and gullying, pioneer species dominate that can quickly regrow after disturbance. So once they are carried away by a debris flow, they just regrow somewhere else, but have a low resistance. So they don't really have to, cannot resist the debris flow well. If we have decreasing geomorphic activity, so a bit more of interval erosion, debris sliding, a bit of slope wash, a so-called establishment threshold can be crossed, and our ecosystem engineered species with this very well adapted traits can start to colonize. And once they reach a certain cover or biomass, they really start to affect the slope movement processes. So this is what we call an engineering threshold. And they prevent slope wash, reduce slope wash, and thereby also change the dominant process, at least in our moraine slopes, to bound solifluction processes. If through their effects the slope really stabilized, we have no process anymore, we found that we have late successional species occurring, and these are actually very strong competitors. For example, they take the light away for the ecosystem engineer species. So a competition threshold can be crossed on the stable slopes, and we don't have any ecosystem engineer species anymore. So basically, we can identify a biogeomorphic feedback window related to low or moderate magnitude geomorphic processes and the occurrence of ecosystem engineer species with these adapted traits. With these conditions, we have a lot of biogeomorphic feedbacks. Okay, so we've been looking at how biogeomorphic feedbacks work through the adapted traits. We've been looking at the conditions of it. So if we, can mountain plants create landforms? And if we look at other environments, for example, in coastal dunes, where you can see here that these Amorphila grass really help to create the small dune. In rivers, we have willow species creating river bars, for example. Is something similar happening on mountain slopes as well? So can we find this also in our in the Turtman Valley where I've been working? And we've been having a close look really at this rock glacier frontier. And if we zoom in, we see this feature with, which is actually turf bank solifluction lobe with vegetation at the front. And we were wondering, what is really the role of vegetation for creating this landform? And could these turf bank solifluction lobes be biogeomorphic landforms created by these feedbacks between ecosystem engineered plants and the effects, the thermal, mechanical, and hydrological effect they have on the geomorphic processes? To investigate this, we really had a very close and long look on 3 solifluction lobes located on an elevational gradient in Turtman Valley. So on Lobi with nearly fully vegetation covered, Lobat, which is fully vegetation covered in the middle part of the slope, and Lobi Ditak on the rock glacier front. And for these lobes, we really had a very long-term UAV measurement survey, so from which we use structure from motion approaches to determine the movement of these 3 solifluction lobes. So what did we find? First of all, I think if we zoom in again to this rock glacier front, we had these steps, and we can also really see here nicely how plants can really produce these steps. So we believe, in our model, we think that really plants can really initiate these solifluction lobes by creating small bulges here through their mechanical effects through their roots and by trapping sediments here. If we then look at the lobe with the lowest vegetation cover, Lobidita, and how it moves, we can very nicely see that we have movement here. So we can see the solifluction movement, which is really cool. And we can also see that there's no movement at this vegetated riser. So I think we can really say that, the vegetated riser, they stabilize the lobe at the front, and they kind of keep the sediment behind it in check. So they can really help to create these lobe threads, where the vegetated riser here can really help to create the lobe threads. If we then look at the partly or mostly vegetated lobe at the lowest part of the valley, we could see that we still had a bit of movement, mostly at the lobe front. And this is actually where also we had a lot of this ecosystem engineered dries, Octopetala. So it could be possible, but we still have to check this, that vegetation can also promote solifluction movement by promoting deeper and thicker ice lenses through the thick organic mats, but we still have to check this. If we then go to this fully vegetated lobe, we see that there's a lot of strange movement, but no real downslope movement. So this lobe seems to be really stable, and we did find a lot of shrub species on this lobe as well. This suggests that there is a stable lobe stage characterized by shrub species, which is either stable because, for example, the shrub species anchor the soil, or also this organic mat of the engineer might have gotten too thick for any freeze-thaw action to occur. So I think based on what we saw, there is evidence that plants influence the development of landforms, these solifluction lobes, but I think there's more to be looked at because it's a really complex process. Okay, so we now know how the feedbacks work for the conditions, what they do. So this suggests that we have a lot of feedbacks, and this could also mean that maybe the geomorphic and ecological development mountain slopes are coupled. So we have a linked change from active slopes to non-active slopes with vegetation. And we've been checking this actually in Muller Glacier foreland in New Zealand. So we're changing the scene a bit now. And the Muller Glacier foreland, yes, you know, as glaciers retreat in glacier forelands, we have periglacial adjustment by different geomorphic processes. We have dead ice melt, the moraines are getting gullied, but at the same time, we also have vegetation succession here with retreating glaciers. So we're wondering if these processes are connected. To investigate this in Muller Glacier foreland, we again did look at 2 × 2 meter plots, 55 of them, noted which geomorphic processes occur and which plant species occur. And using multivariate statistics again, we found that we really have close linkages between changes in species composition and decreasing geomorphic activity on our moraine slopes. And this suggests that we actually have something called a biogeomorphic succession here. This was first described for rivers by Corin Blitt and colleagues. In this biogeomorphic succession, we can identify 4 phases. So in a geomorphic phase, we have really strong geomorphic activity by gullying, by debris flows, by soil erosion processes. Once this activity decreases a bit, we can enter a pioneer phase where these small pioneer species can establish. And with this further decreasing geomorphic activity, we can really enter a so-called biogeomorphic phase, where all these biogeomorphic feedbacks from the engineer happen and where the ecosystem engineers really stabilize the moving slopes. And once they're stabilized, we have a change to an ecologic phase with shrub and tree species in which biotic feedbacks dominate. So for example, competition. So I think we really have evidence that, ecologic and geomorphic development are closely coupled on moraine slopes. So what about mountain slopes in general? And there I cannot really present a concrete answer. I think there's evidence that similar processes happen on part of the mountain slopes, like alluvial fans studied by Lane et al., or on tailor slopes, where we also have strong stabilization by vegetation, and here also development of vegetation. And there were also biogeomorphic succession dynamics found on smaller scales on forested slopes in lower mountain ranges. So there's evidence for this close coupling, but I think there still needs to be more work done.
A few minutes.
Yeah. Last slide. Okay, so I'd like to answer my question now. What do plants do on unstable slopes? Through adapted traits, these mountain plants can act as ecosystem engineers, as we saw, that survive and affect moderate to low magnitude geomorphic processes, and thereby they can contribute to the development of landforms such as our solifluction loaves. So closer look, we need more closer into that. And they can also closely couple geomorphic and ecological development in a biogeomorphic succession, which also needs a closer look besides molatter moraine slopes. Based on all these findings, I'd like to end the talk with an idea that mountain slopes could potentially also be so-called biogeomorphic ecosystem. So biogeomorphic ecosystem, that's an ecosystem in which a structure and functioning of the ecosystem, so also from a geomorphic point of view, sediment transport point of view, is really controlled by these biogeomorphic feedbacks. And this such as in rivers or on coastal dunes, and possibly mountain slopes behave in a similar way, but we also have to make more research on this. So I'd like to thank you for the attention. Thanks to a lot of people for help in the field and for funding.
Thank you very much. So good afternoon, everybody. My main research interest is to better understand pattern and rates of mechanisms involved in the sediment cascade, and more specifically, to quantify sediment fluxes in mountainous environment. Before talking about landslide and numerical modeling, I will first take this opportunity to present an insight of the past work I did about sediment fluxes and connectivity over different spatiotemporal scale, which is in fact the main motivation for me to currently work on denudation rate numerical modeling. Well, as you are certainly aware of, landslides are a dominant source of sediment and a main driver of landscape evolution. However, the timing of the sediment mobilization on a hill slope and evacuation to the river system remain poorly constrained. Sediment fluxes in landslide affected catchment are episodic and controlled by the timing and the duration of sediment connectivity between hill slopes and channel. And this is the case in different geomorphic settings. For instance, in mountain ranges struck by high magnitude earthquake, triggering thousands of landslides at the same times, or in an environment where landslides are more gradually triggered over time by seasonal variation and in precipitation or snow melt. On the left-hand side of this slide, I depict a reactive landscape that are connected to the river network. However, the situation might be opposite. An important share of coseismic landslide material may also remain on hill slope for several years after the initial mobilization. On the right-hand side of the slide, you are looking at an aerial picture of the lower part of the Shimbrick earth flow located in the central Swiss Alps. And the question I asked myself the first time we went on the field there were, how this particular landslide affect the sediment dynamic of the catchment? Is it connected to the river stream nearby? And if so, can we detect its signature in sediment sampled downstream? And we will see that in addition to the landslide sediment dynamic, the landslide sediment dynamic may also cause a methodological constraint to compute long-term denudation rates. And to answer this question, we quantified sediment fluxes over different time scale for this earth flow itself, but also at the regional scale. And for this earth flow that you see on the picture, at the annual scale, I quickly tell you that we showed that the sedimentary distribution on hill slope is very intense, but does not lead to massive sediment export to the river stream nearby. This landscape should therefore be seen as buffered. Sorry. Then we computed sediment fluxes at the millennial time scale using cosmogenic nuclei from river sediment samples. As you can see on the map, sample points are depicted by black and orange dots. The orange dots, are the ones who are in the catchment affected by the earth flow. And long-term, we computed long-term sediment fluxes, which shows a positive correlation with the downstream distance, as you see on the graph on the left. And there is a 2 order of magnitude increase between the first order river catchment and the outlet at the regional scale, and that corroborates the efficiency of sediment evacuation at the millennial time scale. In addition, when comparing timescales over the same spatial extent, so only for the orange dot on the map, so for the earth flow catchment, we see that there is a 2 order magnitude difference between the decadal sediment flux depicted with the star marker and the millennial millennial values. In other words, the last millennia trend in sediment yields do not capture the high rate of the decadal geomorphic activity for this first order river catchment. And this example illustrates how complex sediment connectivity is and the stochastic character of landslide processes. Now, instead of plotting sediment fluxes against downstream distance, here we display long-term denudation rate. We quantify up to 2 order of magnitude difference in denudation rate between the landslide affected catchment. It is marked with stars also, black stars on the graph, and the rest of the study area. The denudation rate decrease with the catchment area suggests that the material initially displaced by the earth flow is not directly evacuated to the river network, but remains on the slopes. And the signal of the landslide is only visible locally and quickly smoothed when going downstreams. From a methodological point of view, mobilized sediment by the landslide perturbs the cosmogenic radionuclide signal measured in river sediment. While it is useful in this case to assess the sediment pulse propagation through the landscape, it has implications for measured denudation rate with this methodology. And indeed, long-term denudation rates nowadays are often quantified using cosmogenic radionuclides. So I will briefly describe the method for those who are not familiar with. So this technique relies on 2 basic assumptions. First, there exists a secular equilibrium between the production of 10 beryllium in quartz grain present in the upper layers of the Earth's surface and their loss by erosion and radioactive decay. Second, the river sediment is sufficiently well mixed, and all parts of the catchment are delivering sediment in proportion to the denudation rates. If these 2 assumptions are met, then the 10 barium concentration measured in the river sediment at the outlet of a catchment is inversely proportional to its denudation rate, that average over timescales of 1,000 to 10,000s of years. But in mountainous environment, and this is the case in the result I just showed you, landslides are excavating deep-seated and shielded sediment that have low concentration in 10 beryllium. And these sediment enter the river network, and with a lack of efficient sediment mixing, it will dilute the 10 beryllium concentration in the river. And subsequently, when we compute catchment average denudation rate, we will get an overestimation of the actual value. So we can ask ourselves if we can trust denudation rates in landslide affected catchment, and therefore our research question, is to which extent landscape and landslide parameter constrain variability and overestimation of CRN-derived erosion rates. And our aim is to answer this question from a theoretical point of view using numerical modeling. Indeed, numerical modeling efforts already highlighted several drivers of CRN concentration dilution due to landslides, with studies by Niemi and colleagues in 2005, Brian Yanites and colleagues in 2009. They explored the influence of catchment area, background erosion rates, landslide erosion, and frequency on CRN concentrations. Basically, they modeled the evolution over time of CRN concentration in simplified landscape, as you see on the picture. And these landscapes are affected by landslide at each time step. To tackle our research question, we started from the work of Yanites et al. And refined the model in several ways. First, we used magnitude frequency distribution to constrain the landslide occurrence in the landscape. So landslide, so magnitude frequency distribution are these kind of graphs where we plot the landslide area against, you plot probability density for several areas of landslides. And typically you have two types of distribution, the power law distribution in light blue and a thresholded version in yellow, and the inverse gamma distribution in dark blue. So we implemented in our modeling framework the inverse gamma distribution, which is quite popular in the literature. So we thought it was it was interesting to do that. A second improvement is that we constrained this magnitude frequency distribution based on landslide mobilization rate, which is the amount of sediment mobilized per square kilometer per year by landslides, instead of using a landslide frequency. Here you see an example of the model. At each time step, sediment is removed from the landscape by background erosion, that is uniform erosion over the entire area, and by landslide erosion. Eventually, sediment removed from the landscape at each time step have a given 10 barium concentration that is further used to compute denudation rates. As you can see here on this snapshot, the concentration within the landscape are affected by landslide, but the spatial pattern and the absolute values are driven by the magnitude frequency distribution that we use as an input. On the left, you have the inverse gamma one, which generate relatively a lot of large landslide in comparison to the power law distribution, and this has important implication because large landslides are deeper, which means that they will excavate more shielded material in terms of CRN concentrations. And consequently, the dilution at the outlet will be greater. We run the model for hundreds of scenarios that result from the combination of three key parameters, catchment size, background, and landslide erosion rates. And and catchment size ranges from 1 to 100 kilometers, whereas erosion rates are constrained based on the value found in the literature. In addition, to assess the variability of these CRN concentrations, we iterated each scenario 100 times. Yeah, well, and so you see a result on the graph on the left. You see the 100 iteration for a scenario characterized by a prescribed background erosion rate of 0.1 millimeter per year and a landslide erosion rate of 0.5 millimeter per year, which correspond to a mobilization rate of 500 cubic meter per kilometer per year. And so we plotted the volumetric erosion rate against the CRN-derived erosion rate computed at the end of the model run. And here we see that it's very interesting to iterate the model, because starting from the same initial conditions, we have a lot of scatter, especially for small catchment areas. So the light purple dots that's on the graph, and for larger catchment areas, so the darker dots, the variability becomes negligible. Then we quantified also the overestimation of the CRN-derived denudation rates in comparison to the volumetric erosion rates. So we computed the ratio between the two values, and with that metric we can assess which setting in terms of landslide and landscape parameters. So which setting provide high probabilities that the computed denudation rate is impacted by landslide occurrence. And this and here on the graph, so on the right, so we have several settings. So the catchment area is increasing when you go on to the right, and you also have several landslide erosion rate values. And so the overestimation decreases with when the catchment area increases. That is quite logical, but we also see that the variability in the overestimation is quite high for a small catchment, and then decrease for larger catchment, but also regarding the importance of landslide processes in comparison to the background erosion rates. So in conclusion, our results corroborate findings from previous studies. Indeed, CRN-derived denudation rates are more accurate when landslides is not a dominant process or in catchment larger than a few dozens of square kilometers. However, by replicating the simulations, we can quantify the overestimation associated to specific landslide and landscape settings. Moreover, we implemented a flexible numerical framework to enable to explore diverse landscape configuration, and that can be deployed on supercomputers to decrease processing time. Finally, we acknowledge that additional work is required to compare modeling results with field data and go a step further to include more complex element connectivity settings. Well, thank you very much for your attention.
Yes.
Okay, thanks. So hello, everyone. I first want to thank the International Association of Geomorphologists for organizing this event. So I'm Pierre Pouzet, and I will present recent research which aims to reconstruct historical storms and marine flooding using sedimentological methods, a research carried out in collaboration with the work of climate historians. And the principle of the sedimentological approach is based on studying coastal depositional environments, which are usually lagoons, coastal lakes, or sea marshes, located behind the protective dune. And the continental sedimentary fillings usually brings many silty or clayey sediments. And during an intense storm, strong marine weather phenomena such as swells, wave, or winds will cause coarser marine sediments, usually composed of sands, back into these coastal marshes. And sediments accumulate on top of hanovers in these environments, resulting in one or more marine allochthonous deposits to the marsh that can be clearly distinguished from traditional lagoons deposits. And these marine layers can be detected in a sedimentological core. As you can see on the photograph, some levels stand out extremely well, and they will be dated so that we can assess their filling period. And to apply this method, we answer three main questions. Once the core is removed, we first ask ourselves, how can we identify the marine layers and how distinguish them from the continental layers? The methodology combines several disciplines and crosses fieldwork and laboratory analysis. we used the different types of cores depending on the soil type to collect the samples, and then several methods such as particle size, organic matter, colorimetry, radiography, geochemistry. And these indicators allow us to cross-reference these proxies and detect the marine layers. And statistical analysis determines the source, the precise source of the sediment. We cross-reference these sedimentological indicators after to select those that are the most relevant for detecting non-native marine deposits in coastal marshes. We carry out an ACP and dendrogram study to find out the geochemical ratios typical of a marine environment. And for example, strontium characterizes a marine environment, titanium and continental environments, so peaks in strontium and titanium core curve will highlight a strong dominance of a marine environment. And once we have detected the marine layers, we then ask when it was deposited. And isotopic dating conducted with radiocarbon, 210 lead and 137 cesium led us to estimate the age of all identified facies. And we note here for the two Atlantic environments, the Trait du Croisic and Petite Mer de Gavre lagoons, the cesium peaks refer to the Chernobyl accident in 1996 and the nuclear weapon test of the 60s. And finally, we then cross-reference the dating of the identified marine layers with historical data. These archives are the key to link our data with ocean storms, and we try to answer the last question, one of the most important: how can we make sure that these marine layers come from a past natural hazard? And I will now show you an example applied to a recent study we conducted in the two lagoons of the Trait du Croisic and Petite Mer de Gavre that are mapped here. And let's talk about the result now of the coring carried out on the Trait du Croisic. And using sedimentological indicators permitted the extraction of numerous marine layers from sedimentological cores dated with the isotope of carbon, caesium, and lead. And variations in grain size and geochemical index clearly highlight this marine facies, which you can see here in yellow. And marine indicators are the average grain, because a strong mean grain indicates an environment composed of sands, unlike clays or silts that are weak, that have weak mean grains. Lightness also, which indicates a clear sediment, and calcium, strontium, and silicon are geochemical elements respectively present in shells, sponge, or sands. And on the opposite, zinc, titanium, and iron are predominantly continental elements. And let's focus on the clearest case on this core, 1972. Here is the sandy layer, as you can see here, surrounded by mud, also visible on the radiography. And this marine layer is clearly identified. And the average grain size, which you can see here, strontium, silicon increase very widely. The lightness much more slightly, while on the other side, the organic matter, the zinc, iron, titanium, and magnetic susceptibility, which is on the right here, all fall. So we are certain that, that this is a marine layer. And we must then cross-check the sedimentological results with historical data to make sure that these marine layers have been driven by a possible external event. And we can date this event precisely with historical records, but also assess human, economic, societal, or natural impacts. And to illustrate this point, I will take a much more older layers that was dated 35 before present in this core, so around 1315. And we note that sedimentological impacts have also been identified at several sites located in the northern half of the French Atlantic coast. Based on the historical record reviewed, we concluded that these impacts could be linked to an extremely destructive event estimated during the winter 1351-52. Here are some elements from the work of many historians. The island of Ré was largely flooded, as were the salt marsh of Olonais and the island of Noirmoutier, whose submersion most likely lasted nearly 50 years. And the weather remained for so long that people mentioned in history book that there was a time when the country was not occupied by the sea. And Atimon's thesis synthesizes this information and describes these impacts as major. This event seems to have been one of the most violent and dramatic weather events of the last millennium on the French Atlantic coast. And thanks to historical work, 19,691 French historical records were reviewed from 14 French archive centers. And 128 storms were recorded, as you can see on this graph. But we must keep in mind that this is a non-exhaustive work, and some time periods show a significant lack of information. This type of analysis allows us to discuss the impact of storm on a broader scale. The table here reviews the sedimentological impact listed in published studies. And the maps shows and specialize the data from the 5 major storms studied to assess their spatial amplitude. And while this work is of course non-exhaustive, we need to assess the spatial extent of the main event that occurred during the last millennium based on data collection from many geophysical or historical sources. And why is it important? We can offer some hypotheses on the evolution of trajectory in the Northwest Atlantic basin from the standard trajectory defined by Lozano here on the left. And in our study area, 2 types of trajectories are identified. The first in a west-east direction, zone 3, and the second from the southwest to the northeast, this is zone 4. And if we compare with our specialized data here, we can notice that the event of 1644 could follow the zone 4 trajectory to the northeast, while the event of 1469 could rather have a west-east direction of the zone 3. And we then can synthesize the information to understand what influences these events. The collection of all these impacts is summarized in a table containing all study, you can see here in the line here, A, as well as the other that were carried out in the northwest of France. And specific extreme events are shown in green, with the arrows corresponding to their error margin. These data are compared with storms detected only in historical archives. This is a graph that I've shown you before. And as you can see, the 3 phases indicated in blue show sedimentological record, highlighting storm phase in a wide part of the French Atlantic coast at the same time when historical archives exposes a significant peak of storm records. However, several limits are highlighted, and historical sources cannot underline the complete chronology of storm records. And these data are compared with 4 temperature evolution curves in the northern hemisphere from the latest IPCC report. And we can note that the 3 stormy phase appeared to be linked to climate cooling periods. And finally, we also have taken 3 evolution curves of the North Atlantic Oscillation. And the main trend related to this curve is represented in red for positive phases and in purple for negative phases. And from these various observations, it seems that there were more impacts recorded during the positive phase of the North Atlantic Oscillation during the last millennium in the northwest of France. But we have to be careful. We cannot directly link the activity of the storm in the last millennium with the positive phase of NAO and climate cooling. We recognize that being in the extratropical region, it's a limit to our study. Storms are of lower intensity than in tropical areas, and they must be crossed with a high tide to cause a sedimentological impact. So weather marine parameters must be combined There can no be links between the pure climatological storm formations and these different observed influences. As a perspective, we also tested an original dendrochronological approach to detect past wind events. We call the Pinus-Pinaster stand, which is located in a coastal dune. And here is an example of a comparison between the two radius C and D of the correct trees. Radius C being the one from which the wind comes, which will be compressed, and D being the one that will be relaxed in the other part, in the other side of the axis. And when comparing the width of the rings, we notice that when the tree grows straight, they are roughly equivalent. And when an event occurs, the C-axis show wake width, while the rings are wider in D. And we built a precise methodology, and the stormy years at the entire dune stand scale are considered with the index of storm disturbance corresponding to the number of impacted trees on the number of living trees. So it's a rate, a number of impacted trees on the number of living tree rate. And to certify our model, we compared this tree ring analysis with a meteorological database compiling recent storms. And we then show the compatibility between historical data and the dendrochronological result year by year. A year is considered compatible if a tree ring disturbance is detected during a storm year, or if there is no disturbance during a storm-free year. And overall, over the 61 years covered by the dendrochronology, there were 80% of compatibility, 10% of uncertainty, mainly due to the undefined impact of some storm on the study area, and 10% of incompatibility that were explained in our study published in Ecological Indicators. Well, thank you for your attention, and please do not hesitate if you have any questions.
So hello everyone. I'm going to take you a bit further away to Madagascar, which is located just east of Africa, where we focus on the highlands which are located in the center of the island. And these highlands, they are characterized by a very specific geomorphic phenomenon. They are called lavaka, which means gully, which means hole in the Malagasy language, which are very large gullies, which are typically inverse teardrop shaped. They broaden uphill, they have small outlets, and they can be very deep, also because you have very deep soils in Madagascar. And as you can see from the satellite image, they can really be very densely present in the landscape. So we have these very high densities. We also have a lot of grasslands in the highlands, and this led to the narrative where you had Madagascar as a fully forested island, and then when humans arrived, they deforested it, leading to a human-induced environmental crisis. However, recent research has shown that grasslands are endemic. However, their extent might have changed, and it is also clear that lavaka were already present in this landscape long before humans arrived. So they seem to be a natural feature of this landscape. What's, however, not clear is whether the amount and intensity of these gullies has recently increased and if this can be linked to human impacts. So therefore, we formulated these main objectives. So we wanted to see if the current system is out of equilibrium. We wanted to develop a formation time frame to see when they were formed. We also tried to model these lavaka using a population-based approach in which we try to relate then these dynamics to environmental drivers. And we also try to quantify current mobilization rates and to link these with long-term denudation rates. So I will first give you a very, very short overview of environmental changes in the highlands based on the literature over the past 2000 years. So we know from pollen that grassland areas did increase over time. So they started to increase a bit more than 1000 years ago, and they further increased 600 years ago. We also know that there have been some climate variability with some drier periods 1000 years ago and also more recently. We also know that humans only arrived very recently in the Central Highlands. So we have permanent human settlements since more or less 1,000 years ago, maybe a bit earlier, which is very recent. And we also know that cattle was introduced around the same period, so also pretty recently. From DNA and from more current sources of information, we know that the population started to increase for the first time 1,000 years ago, and then more recently we really see an exponential increase in population growth due to the demographic transition. So if we would add up all of these different environmental factors, you could come up with a sort of overall environmental pressure curve, which is accelerating and increasing throughout time. If you would add up all of these factors of changes in vegetation, human population growth, cattle, etc. So what did we do? We focus our research on the Lake Alautra region, which is located in the northeastern part of the highlands, where we selected 6 study areas of 10 to 15 square kilometers. And for these areas, we have historical aerial imagery from 1949, 1969, and imagery from now. And we also sampled some floodplains. So the floodplains are indicated by the red line. So we have 5 transects that we sampled, on which we have 14 radiocarbon dates. And what you can see here is just a movie. So we digitized the outlines of these gullies to see how they change over time. So this is 1949 and now, and you see that in the red encircled areas, you have some pretty strong growth that you can see over this period. So this is just another example. So we digitized the extent of the lavaka to have an idea of their areas and how fast they are growing. Then we also try to get an idea on the volumes of these features. So we did this by taking the difference between the current elevation surface, then we interpolated this surface, and then the difference, get an elevation. If you multiply this with the area, you get a volume estimate. And we then established a relationship between the area and the volume. And then because we have the areas from the lavaka in 1949 and now, we can also calculate the volumes. And in that way, we can get an estimate of the amount of sediment that gets mobilized over the past 70 years by these gullies. So the first results, so first we looked at the current equilibrium. So we looked at, for our study areas, at the amount of lavaka that were born, so that appeared over time, and at the amount of lavaka that were stabilized, and where we define stabilized when the extent did not significantly increase, when the bare surface decreased, and when there is more than 95% coverage by vegetation. And then we looked at the ratio of the amount of lavaka that appeared and the amount that stabilized. And so this ratio is indicated by the gray dots. And you see that for all our study areas, we have ratios between 1.7 and 35 with an average of 6, which indicates that in our study areas, we currently have much more new gullies that are appearing than gullies that are stabilizing. So we have a growing population of gullies, so to say. Then a second thing that we did is we tried to get a sort of time frame of when these gullies appeared in the landscape. So we first calculated the age of each gully based on the growth rates that we observed and the current areas. And then we found that the gullies in our study areas are more or less 350 years old. And we also tried to get an estimate of the timing since the onset of increased activity, which we did based on the observed birth rates, stabilization rates, and the number of lavaka. And then a bit depending on the assumptions that you make, we end up with an onset of increased activity between 400 and 900 years ago. So this is just for 6 study areas, of course, but we also have these floodplain data. And what we see there is, when you look at the second graph, is that the long-term baseline floodplain sedimentation rates range between 0.5 and 2 millimeters per year. And then we see a first slight increase around 1,000 years ago. And then since more or less 400 years ago, we see that these floodplain sedimentation rates seem to be increasing quite strongly up to 35 millimeters per year, which is 5 to 15 times more than this baseline value that we have. So if we summarize this, we see both for our calculated timing based on the lavaka data that we have, and for the floodplains, we see that we have a first increase in erosion 1,000 years ago, and this seems to further intensify 400 years ago. And if we then go back to our framework of environmental changes, this more or less corresponds to the first timing when humans arrived in the landscape, and when we also see these first changes in vegetation. And then this further intensification corresponds to the period where we have a drastic population growth and also further changes in the vegetation in the landscape. So what we try to do next is to better understand how these environmental pressures might affect the gully population. So we really try to model the gullies by taking a population approach. So really like you would do with the human population, we know how fast they grow, which depends on their surface area. We also know when they die, so when they stabilize, which we can also base on the areas of the stabilized lavaka that we have. And then to model the birth rate, we make it dependent on different environmental pressure levels. And so we try to model 3 different scenarios. So a scenario where you have a linear increase in environmental pressure over time. So when you just have a gradual increase in the pressure. We take a logistic scenario, which then more corresponds to what you would expect if the environmental pressure mainly depends on vegetation changes, because in the beginning there will be a lot of deforestation, and then towards the end there will be less forest left, and this will slow down a bit. And then the third scenario is more based on what we concluded from the literature. So that's a scenario where we have a recent acceleration in environmental pressure. So that are the 3 scenarios that we tested. And then, so we model how our lavaka population is evolving. Now, when we look at the number of lavaka that we observe, so the black dots are what we observe in our study area. So we have around 700 lavaka now that we see. And so you see that the first 2 scenarios, so the linear and the logistic increase, they show a strong overestimation in the number of lavaka, whereas the accelerating scenario, we have a slight underestimation. And then more importantly, we also modeled, or we could also calculate then this ratio of the amount of lavaka that are born compared to the amount that stabilize. And when we look at this, we again have in black and in gray, we have the observed ratios. So the one of 6 on average for our study areas. And then you see that only when you have a scenario with a more recent accelerating increase in environmental pressure, only then you get the ratio that is close to what we observe today. So this seems to suggest that that the disequilibrium that we see today is caused by a more recent change in environmental pressure. Then we also have the data on the lavaka mobilization rates. So we have, for the different study areas, we calculated the amount of sediment that was mobilized over the past 70 years, which ranges between 18 and 300 tons per hectare per year, which is quite a lot. We also have reservoir sedimentation rates for the study area, which are already lower, but still comparable to the lower mobilization rates that we find. So this already seems to suggest that there's quite a lot of sediment that is stored near the gully or in the floodplains, and it's not reaching the rivers or the lakes. However, when we then compare it to long-term erosion rates that we have from beryllium data in the rivers, these are almost 100 times lower than the rates that we observe now. So these range between 0.16 and 0.5. So this again seems to suggest that there has been a recent increase in the amount of erosion that we see in this landscape. So if I try to summarize all of this, 2000 years ago, we had a landscape where there were few lavaka present. where we had low floodplain sedimentation rates and also low background denudation rates. Then around 1,000 years ago, we see the first humans and cattle appearing in the highlands. We also see a first increase in the floodplain sedimentation, and we estimated then that that you start to have this growing number of lavaka. You also have a drying climate. And then if we would summarize the current situation, we see that there is an acceleration in the pressure, where we have much more cattle and people living in the highlands. We also have more deforestation. We see many new lavaka appear. We have high floodplain sedimentation rates, and we also have high current lavaka mobilization rates. So if you would like to read more about this, we have just published 2 papers about this, where you can find some more information. And I am very happy to answer any questions.
Thank you, Candy. Thank you, Emmanuel, as well, and Suzanne for the organization of this session, and thank you to the EAG for organizing this week event. So I will present you some work about Mediterranean hybrid urban deltas. Before to start, I want to say that this work is not possible without interdisciplinarity, without archaeologists, geographers, human geographers, engineers, archaeologists, historians, and also all the institutions and funding programs that help to build up this research. So I present you two deltas related to 2 systems, the Francoli Delta, which is in Spain, and the Tiber Delta, located a few kilometers downstream of Rome in Italy. So there are 2 different systems. You have on one side the Francoli Delta, which is very small. It's only 8 square kilometer delta. And on the other side, you have the Tiber Delta, which is much bigger, 180 square kilometer. One thing in common, which is interesting, it is the highest reconstructed historical flood event. They are very high, and especially for the Francoli Delta, it's related to the flash floods, the very huge flat floods of the Catalonia coast that are very destructive. And you can see that this event can be similarly catastrophic for both of these areas and geomorphologically morphologically active. The specificity of these 2 deltas, there are 2 different systems in size, but they are very urbanized. Tarragona developed all around the delta, and also especially in the pro-delta of the Francoli Delta. Tarragona developed a huge harbor towards the sea at the mouth of the river. And in the Tiber Delta, you have the international airport of Rome that occupy an important part of the delta. You have also intermodal platforms between Ponte Galeria and the airport. You have also important urban areas, Fiumicino, Sedilito, Fregene, that are all along the coast. And the specificity of these deltas, they are also that are occupied for a long time. The Tiber Delta was hosted 2 important city ports during the Roman time, Ostia and Portus, that were built between the 4th and the end of the antiquity, 4th century BC to the end of the antiquity. And Tarragona was the first Roman settlement in Italy, in Spain, developed also a lot after that during the Roman period. So generally, when we want to study deltaic plains, we study beach ridges, we date them, and we start to understand why there is this progradation and the pace of the progradation, the rhythm of the progradation. And we try to understand it at the first level in relation with the watershed, its land cover, its land use. And also after, to try to also to reach a wider model to know if it's related to paleoclimate forcing, and to try to see like similar trends between paleoclimate and coastal mobility. But for studying urban deltas is much more complex than that. We should take into account also the socioeconomic context. On one side, you have the geoscientific approach, taking into account the source to sink approach with watershed, delta, and sea, where the delta is really in between coastal and fluvial processes. And also take into account the city and the urbanization of this delta, but the city taking the city part itself, but also the harbor and the development of the harbor. And this is related to a network, to a development where you have not, in the first interpretative system, sediments and water are moving around. In the second interpretative system, in the socioeconomic context, you have people and goods moving. And what we will see together is to try to see the interaction between the two. In the first model, you have indirect man-made delta in the sense of Maselli in 2013 that identified during the Little Ice Age that actually the progradation was partly due to human activity in the watersheds, but also taking into account locally the direct man-made delta today, also the past. Here you have an image of the Francoli Delta in the middle of the 20th century, where you have the city and the delta next to each other and starting to overlap. First, we will talk about the Tiber Delta in a long-term perspective. But for understanding a delta, it's better to take into account recent periods. So we will see first the recent period and after go back in time. The methodology is very classic. We use morphological data, so it can be geomorphological data, features of a river, of the coast, but also archaeological features related to structure, etc. On the other side, we study stratigraphies, we do core drilling along the coast, and we study paleoenvironmental context, and we date this core to fit within absolute chronology. So the data set are very important for the Tiber Delta, and we can reconstruct the evolution of the coastline during the last 500 years. What is interesting is it's this map at the bottom here from Catastale ad Alexandrino, where it's a map of the beginning of the 17th century. And actually, generally, it's very hard to do georeferencing, but here they provide all the information of the geometries that they calculate on the field. So we know which point on the size of the different elements of the landscape, so it's much more easier to georeference. So here it's the river mouth of the Tiber. You have at the south the Fiumara Grande, which is the natural river mouth of the Tiber. And the Fiumicino is originally a canal built by the Romans. And actually, it modified, since the Roman period, for 2000 years, it modified the morphology of this delta. And what is interesting here, it is, we see with the little dots here, you have the reconstruction of the coastline in the beginning of the 17th century. And since then, as you can see, there is not so much mobility of the main river mouth of the delta. You have a dynamic stability. It moves a lot. There is lots of sediment coming, but lots of sediment also that are removed and eroded. On the contrary, to the north, the Fiumicino, you have a strong progradation for the last 400 years. What's happened, it's like you have sedimentation mainly at the mouth of the Fiumara, and after you have redistribution of the sediments along the coast towards the south and towards the north due to littoral drift. And after, the river mouth to the south is not managed, but the Fiumicino was always used for the last 1,000 years for navigability. So it was managed and was used passonate, they call in Italy passonate. They are construction of woods that are built towards the sea and that are protecting the river mouth from the silting up. But actually, it also trapped the sediments on both sides. And finally, they had to build and build and build passonate through times. And finally, this deltaic plain is man-made because of the construction of this passonate and change a bit the morphology, the general morphology of this area. During the 16th century, you have a huge progradation, finally, that is in the Fiumara area to the south. And this was due to major floods that were mainly flash floods, that were summer floods, and also one major winter flood at the end of this century. And you have almost like 4 kilometers of progradation during this century, which is very, very important. So it's interesting to see that, to interpret that in relation to Little Ice Age, and to see that morphologically, it was really the 17th, 16th centuries that were very, very morphogenic naturally. And after, it's more difficult to know the interrelation between climate influence and also the influence of humans stopping the sediments. So if we come back in time, what will we record? What is important, as you see, it's to be at least the closest from the river mouth. The closest you are to the river mouth, the closer you have chance to have progradation. The further away you go to the river mouth along the coast, you have maybe sediments that are related to erosion. You record erosion far away from the river mouth, and the closer you record mostly progradation. So the location of the cross-section you study is very key. So let's have a look now to the Roman period, and especially to the area of Ostia. During the Roman period, a city was built really at the mouth of the river Tiber. And what is interesting, within this city has been excavated widely, so this is very interesting to study the urban fabric of this city. We can see that this city actually recorded fluvio-coastal change through times. It recorded fluvial mobility in blue, and also it recorded in the urban fabric coastal mobility. And in between, you have this district that is in pink on this figure. So if we study 3 cores that have been drilled from the city center of the city towards the river mouth, along the river mouth course, river, we can see in these 3 cores that actually between core CAT2 and OST4, you have a strong progradation that happened between the 8th and the 5th century BC. So very strong, similar to the one of the 16th century, beginning of the Little Ice Age. And after that, you have like sedimentation that slow down, it seems, and we have maybe a gap. And after we have sedimentation for the end of the first millennium BC. After, if we look at the river towards the north, core MO3, 1 and 2, we have a record of the migration of a Paleochannel. So we record a migration of the Paleochannel from the 4th century BC to the 1st century AD. And so we have this screenshot in time where you have the mobility, and after the sedimentation, the lateral mobility stopped. This is very interesting because actually this Paleochannel was functioning until the 16th century when it was cut off. So in a recent paper, we published a synthesis of the first millennium, the dynamics of the first millennium, where we see we have a strong progradation in the first part of the first millennium BC, maybe a second one also during the 4th and 3rd century BC. And between this period of strong progradation, we have phases of erosion that we record a bit more further away from the river mouth. These are mostly related to main events, main hydroclimatic crisis, but also may be related to more activities within the watershed of the Tiber. But what happened between the 1st century AD and the 16th century AD? We have the stability, which is very surprising in such context. So the stability in the river, but also we have during the late antiquity, we have something that happened along the coastline. We have record of erosion, lots of erosion from 2nd, 3rd century AD. So this is very surprising. We record it also in the sedimentation of the cores. Here we have a core along the coast, and we have like a very active beach here that was dated with the archaeological facts to the 1st, 3rd century AD. What's happened here? It's maybe not all related to climate, because here during the 1st and 2nd century AD, Romans built many canals at the river mouth of in the Tiber Delta. And maybe it's possible that Ostia, that was located downstream of all these diversions, maybe less power, less competence on the river, conducted to less fluvial mobility during 1,000 years, but also maybe led to erosion at the mouth of the river during the 1st to the 3rd century AD. So it's very important to take into account local facts and like anthropic impacts on the coast for reconstructing changes and before to go to interpret coastal changing and river changes related to climate. If we go quickly to the Fanconi Delta here, we try to follow a bit the same methodology, but try to go from the past to the current days and try to really bring together archaeologists, historians, geomorphologists, and human geographer, remote sensing specialists. Here we have also an analysis of the urban fabric, and the city of during the Roman period also developed along the river mouth, and after was abandoned during the medieval times and start again during the last 2 centuries. We do analysis also of the cores. We identified 2 harbor deposits, one during the Roman period in unit C at the bottom, where you have like mostly fine deposit, but also a lot of sand within this harbor. And after, in the last centuries, in the last 4 centuries, you have also harbor deposits with fine deposits that are developing again in this area before to be backfilled by new quays built in the end of the 19th century. I go quick on that. After we tried to reconstruct edge depth model, I very envy people working on lakes or marine areas, because here it's very dynamic environment. It's very difficult to reconstruct mathematically edge depth model. So here you have mostly an edge depth model in steps, considering all the analysis of the stratigraphy, which means that you have period of sedimentation, but also a strong period of or erosion or dredging inside the harbor. But if we connect information together related to this edge depth model in steps, with huge gaps in time, if you take into account also old maps where sometimes you see Roman moles along the coast, sometimes it is trapped within sediments. So sometimes you see it, sometimes not. You have period of erosion and sometimes period of sedimentation at the river mouth related to the infrastructure of the Roman harbor. And after also with georeference map, you have also these processes where at the end of the 19th century, you see the Roman mole after it happened to be filled up, and after again it happened again to be seen in 1820s in the delta. So what's happened here? We have a system that is really a delta with very strong is very strongly event-based. Sometimes you have very strong floods that will fill up your river mouth with sediments on your harbor, and sometimes you have a strong event of storms or like a long period of littoral drift that will erode the margin of the harbor, but also the parts of the river mouth. So you have these cycles of erosion, sedimentation inside the harbor. After we try to connect the data from the past to the data of today. So we try to understand how the harbor evolved and how we can connect bathymetry of the past, bathymetry of today. So we took like 30 maps with bathymetry for the last 200 years, and we reconstruct the evolution of the harbor doing georeferencing, digitization, and after interpolation, and comparing the different periods. What we studied a lot, it was also the georeferencing point. Generally, we georeference and we think it's good. Here, it's the base really of the study to have really good data to georeference. So we positioned all our georeferencing points, and we try to see how long we can follow our georeferencing matching points towards in time. And we see that finally we have only 2 georeferencing points that can be related to the area of Tarragona before the 19th century. Only 2 points. It means before it's very difficult to do georeferencing. And actually each period of when we lose point of georeferencing, it's a period where you have major changing within the harbor. So it's also a proxy of urbanization. Working on georeferencing, it's also a proxy of georeferencing, evolution of the city on the harbor.
You have 2 minutes.
The evolution of the harbor through times. Yes, it's mostly. We have our evolution of the harbor through times. With phases of erosion related first in the 19th century, mainly related to natural forcing, and after during the 20th century, 21st century, mainly related to anthropic actions. And now, really, in the current harbor, you have no more source to sink with watershed to the sea. Now, all the sediments of the Francolí Delta ends up in the harbor, where engineer kind of built like a bucket for sediments, and where they drilled really at the mouth of the river in the harbor itself. And we wanted also to work on chronologies and to cross more and more data together to really understand the period when the harbor was eroded, when it was filled up, if it's related to a paleoflood series, paleostorm series that are related to the area, on the evolution of the urbanization in the area. And here a final image to show how to cross also data from the cores to data from paleobathymetries of ancient maps, to show that we can connect really informations from geoarchaeology to data from today, and really to reconstruct the temporal trajectories from the past to today to better understand the evolution of these urban deltas throughout times. So instead of a classic interpretation of urban deltas, very linear, we think it's very important when you have a long-term urbanized delta to take into account all the factors, and to be careful to interpret coastal changing or fluvial changes only in terms of paleoclimate or land cover, land use within the watershed. Thank you for your attention.